I'm recording. So what we're going to be talking about today is a type of differentiation that's especially useful when it's hard to solve an equation for y or f of x. And it's called implicit differentiation. It's also really useful when you've got things that are changing with time. Okay, so basically think of it as your x's and your y's are functions of time. Okay, the whole concept of implicit differentiation relies on the chain rule, if you remember how that works. When you've got a composite function, you first differentiate the outside function and then you differentiate the inside function and multiply the two together. So we'll be using the chain rule over and over again as we talk about implicit differentiation. Okay, so let's get started by, I'm going to share my browser with you and show you where we are in the course. Okay, so you can see we're in week 9 still. Okay, and I am looking at 2.11, which is implicit differentiation and related rates. Related rates are application problems that use implicit differentiation in order to solve the problem. Okay, so they're not two different things. Okay, you could think of implicit differentiation is the calculus skill that we're going to learn, and related rates is how you apply that skill to a real problem. Okay, so again, if you go down here, you'll see implicit differentiation notes, and that's what I'm going to be opening up on my tablet and sharing with you. Okay, so as always, this takes me a while, so give me a minute to get that done. Okay, and let me share the content with you. Right, we should be in a place where everybody sees implicit differentiation notes. Okay, it doesn't say notes, but they are notes. Okay, and again, to remind you, these are excerpted from the readings. Okay, they don't cover everything in the readings, so I would encourage you, to go through the readings that are in the week 9 module, as well as looking at videos and that sort of thing. Okay, before you try the homework. But again, this should give you a good overview of what we're talking about. Okay, so let's take a look at this equation right up here. Okay. This equation has y's and x's mixed together. And because y is a variable here and an exponent here, this equation is very difficult to solve for y. In other words, it's hard to isolate y on one side of the equation. Okay, so that's called solving explicitly. And what that means is isolate y on one side. Okay, isolate means it's the only thing that's there. Okay, so you've all seen equations like that throughout algebra where it's y equals x squared minus x. That's called an explicitly solved equation. Well, not every equation's easy to get in that form, but sometimes we can still differentiate a function like that. We can find its rate of change, its instantaneous rate of change, basically by this process called implicit differentiation. Okay, so what's the key idea behind implicit differentiation? Well, the key idea is to assume that y is a function of x. Okay, so again, even though you can't see what that function is, right? You can't solve for y, we're going to assume y is a function of x. So whenever you see a term with a y in it, you're going to assume you've got a composite function, right? You've got the y term, which might have a coefficient or an exponent on it, and then you've got the function of x that's inside y, okay? So that's a composition. Okay, so if y is a function of x, then it's a composition of two functions, right? Basically, it's whatever the y outside looks like, and then it's whatever that inside function is. Now, you might say, well, wait a minute. Normally, when I use the chain rule, I can see the inside function. Otherwise, how do I take the derivative of it? It's really easy. Whenever you're going to use the chain rule on y as a function of x, the derivative of the inside function is going to always be dy dx. Okay, so basically, you don't have to worry about taking the derivative of something that you can't see. Okay, so it's clearer when performing implicit differentiation to use dy dx instead of y prime or f of x. Okay, so remember, this is the derivative of y with respect to x. Okay, when we get to the related rates problem, it's going to be very important to notice what's on the bottom, okay, of dy dx. Okay, what variable are we differentiating with respect to? Okay, so far we've only been talking about differentiating with respect to x, but you'll see when we get into the related rates problems later, we're going to be differentiating with respect to time, t, okay? So again, this notation is helpful in a whole bunch of ways, all right? So again, to summarize, to determine y prime, okay, or dy dx, okay? Remember, y prime and dy dx are the same thing, okay? Differentiate each side of your equation, treating y like it's a function of x. Then there's a bit of algebra at the end where you have to isolate dy dx, because that's what you're solving for. Okay, remember, y prime and dy dx are the same thing. Okay, so let's take a look at how it works, because that's a whole lot better than just talking about it, right? So here's an example. Okay, they're saying in the following 5 examples, find the value of dy dx at a given point. Okay, so they're saying here's this function. Okay, it's got x's and y's in it. If we were to solve for y here, we'd wind up with a positive and negative square root, okay, which is ugly. We don't want to have to deal with positive and negative square roots. So let's just differentiate it implicitly rather than trying to solve it for y first. Okay, then once we find its derivative, we're going to plug in the x and y values of the point and find out what the value of the derivative is at that point. Okay, so again, the derivative has the same meaning as it always has. When we get this number, and it will be a number because we're plugging in x and y values, we're finding the derivative at a point. It's going to be the slope of the tangent line to this curve at that point, okay? If this were some sort of a marginal, if this were some sort of a cost or a profit equation, it would be the marginal of whatever y is, okay? So again, the derivative has the same meaning. It's just we're going about it differently, okay? So here's the way you do it. Okay, whenever you've got terms that just have x in them, you differentiate them normally. So my first term is an x term. Okay, I'm going to differentiate it with the power rule. That gives me 2x. Okay, the next term, this one, okay, is a y term, and I want to treat y as a function of x, which again means this is a composition. The outside function is y squared, and the inside function is this y function I can't see. So when I take the derivative of the inside function, y, it's just going to be dy dx. Okay, so I'm going to apply the chain rule here. Okay, so first thing I need to do is differentiate the outside function. That's 2y, again, using the power rule. Okay, and then the inside function derivative is dy dx. Okay, so again, outside times inside. Okay, hopefully everybody remembers the chain rule. Okay, so that's using the chain rule. I have to differentiate both sides of this equation, right? Because I wasn't able to solve it for y. So the derivative of 100 is 0, right? Because it's a constant. And that, folks, is implicit differentiation in a nutshell. Okay, you just differentiate all the terms where they stand. Okay, so rather than doing algebra at the beginning, you're going to do algebra after. Okay, so now we have to solve for dy dx, because that's what we needed to find, was dy dx. Okay, so all I'm going to do is I'm going to subtract 2x from both sides. That's going to put it on the right side with a negative sign in front of it. Okay, and then the last thing I need to do is divide by 2y. And I get dy dx equals negative 2x over positive 2y, or negative x over y. Okay? From here on down is just algebra. Okay? This is the only calculus step. Okay? Everybody all right with that? Let me stop at this point and ask if there are any questions. Any questions? Anybody have anything about this that's not clear? Again, you can unmute, you can type it in the chat. Everybody get the drift of this chain rule step here. Okay. All right. Well, the last part of this was to evaluate it at 6, 8. So I'm going to take dy dx, and I'm just going to plug in the 6 for x and the 8 for y, which gives me negative 3/4. Okay, so again, what that is the slope of a tangent line, okay, over here. Okay, you can have a question about, can I plug the points in the beginning before you do the algebra? Sure, you can do that. Okay, I personally like to get the equation first, because remember, the point of doing plugging in the numbers last is once you get the equation, this is like saying y prime or f prime of x is negative x over y. And then you can plug in whatever values you want. Okay, if you plug in the values first, then you're going to have to do the algebra every time if you want to evaluate this at different points. Okay, so yes, it's perfectly mathematically correct to put the numbers in first, but just remember, if there are multiple points you need to evaluate your dy dx, your derivative at, you're going to have to do the algebra over and over and over again. So my recommendation is to plug the xy values in last. Okay, so it's a recommendation. It's not that it's wrong to do it the other way. Okay, everybody understand that? Okay, it's more general to get the dy dx as an equation with x and y in it, and then you can use it over and over and over again for different values of x and y. Okay, so I guess it depends on what you're going to do with it. Okay. All right, here's another one. Okay, so we'll go through a couple of these so you can get the general drift of how this works. Here's another xy point. And again, you can see this function is difficult to solve for y because of this mixed xy term. Okay, it's going to be difficult to isolate y. So let's just use implicit differentiation. Okay, so let's take a look at the terms before we start. This is just an x term, so it's just going to differentiate normally. This is a product. Okay, I could say negative 3x is my first factor, y is my second factor. right? And in both this term and that term, y is a function of x. Okay, so this is a product with a chain rule inside of it. Okay, so let's see if we can get this going. All right. So I'm going to like label this in red, that this is a product. Okay, if at any point, guys, you don't see what I'm saying, okay, or it's not making sense, please stop the train, okay? Just shout it out or put it in the chat and say, hey, wait, that didn't make sense. Can you go back and explain it in a different way? Okay. All righty. So again, differentiating this implicitly, like where it stands, the first term gives me a 2x like before. And then I have to kind of handle this product rule business. Okay, so I'm going to go over here and I'm going to do the product rule on the side. Okay, and this is the thing I want to differentiate, minus 3xy. Okay, and I'm going to say my first factor, which I'll call u, is negative 3x. My second factor, v, is y. Okay, it's just easier that way to take the coefficient with you. I know some of you are saying, couldn't I just, do x, y? Yeah, sure, but then you've got to remember that negative 3 is there. Okay, and you're going to have to distribute it and all that stuff. So this takes care of it. Just bring the coefficient and the leading sign along with that first factor. Okay, it's easier. Okay, so y prime, u prime rather, is negative 3 because that's just differentiating with respect to x like normal. Okay, and again, v prime, I've got the y, right? The derivative of the outer function is 1. Okay, that's the derivative of y. Then the derivative of the inside function, the y that's a function of x, is just dy dx. Okay, because again, we're treating y as if it's a function of x. Okay, and then as far as the product rule, we've got u times v prime plus u prime times v. That's the product rule. And I'm just going to copy my bits in there. Minus 3x times dy dx. Remember, I don't need the 1. The 1 isn't doing anything for me. I just showed it to you so you know I'm using the chain rule. Derivative of the outside function is 1. Derivative of the inside function, dy dx. Okay, and then the last term, u prime, which is negative 3. Okay, so rather than saying plus, I'm going to say minus 3, and then v. Okay, so here is my derivative of the product. Again, I probably shouldn't put a box around it because it's not finished. This is what's going to go back in here. Okay. So now I have minus 3x dy dx minus 3y. That's the product. Okay, everybody see where that came from? Okay, so there's the product. I'll try to like do something to make it stand out. Okay, so that's just the product. And notice I always write down what I'm doing. Why do I do that? It's not just that I like to write. I don't actually. Okay, but I do that so I don't lose track of bits. If you try to do it in your head, unless you're very, very accomplished and very practiced at it, you're probably going to make mistakes, certainly with signs, if nothing else. Okay, so I recommend you set aside this little work area over here and just do any product rule or quotient rule you need to do. Okay, the next term I'm looking at is 7y. Okay, and that is a composition of the 7y as the outside function, and then the function I can't see, y as a function of x inside. So if I differentiate the 7y, the outer function, I get the 7. And if I differentiate the inner function, I get dy dx. Okay? The right-hand side is a constant. When I differentiate it, I get a 0. So one of the patterns you should see already from doing implicit differentiation Any term with a y in it is going to generate dy dx, right? Okay. In this case, I generated two terms out of the product, and one of them has a dy dx in it. Okay, this y term generated a dy dx. Okay, so it's kind of a sanity check on whether you're doing it correctly. Okay, so that's the calculus step. Okay, the rest is algebra. To solve for dy dx. Now, in this example, you'll notice two terms have dy dx in them. So if you remember solving formulas for one variable versus another, the strategy for doing this is get all of the terms with dy dx on one side of your equation and get the rest of the terms, the ones without dy dx, on the other side. Okay, so I have two terms here and here with dy dx, and I have two terms, the 2x and the minus 3y, that don't have dy dx attached. So these are going to get moved using algebra, right, to the other side. They're terms. This term's positive, so I need to subtract it to get it over here. This term's negative, so I need to add it to get it over there, okay? So what I'm going to do is minus 2x, okay, and then plus 3y, okay, and then minus 2x plus 3y over here, okay? Everybody all right with that? Again, I'm trying to not copy everything over and over because I'm kind of running out of space. Okay, so once I subtract the 2x on the left, you can see those go away. So does the minus 3y, and I'm left with negative 3x dy dx plus 7 dy dx. And on this side, I have minus 2x plus 3y. Okay, everybody all right with that? And if you're asking me, can I write it as 3y minus 2x? Yes, of course you can. Okay, same idea. As long as you take the leading sign on a term with the term, you can switch the order here. So you can also write this as 3y minus 2x. It's the same thing. Okay. Now what you want to notice is each of these two terms on the left have the common factor dy dx. So what we're going to do is we're going to divide it out. Okay. And what that's going to give us is negative 3x plus 7. Okay, so I'm dividing each term on the left by dy dx. Okay, and now in order to solve for dy dx, you need to remember this is a multiply, right, between dy dx and the parentheses. So all you need to do is divide by the parentheses on both sides. And you get dy dx equals minus 2x plus 3y over minus 3x plus 7. Okay. Everybody good with that? So there it is, solving for the derivative. And now they want me to evaluate it at 2, 1. Okay, so I'm just going to plug in the values they gave me for x and y. So I have minus 2 times 2 plus 3 times 1 over negative 3 times 2 plus 7. Okay, so everybody understand what I'm doing here is I'm taking the ordered pair they gave me, the point on this curve, and I'm evaluating the derivative at that point. Okay, so this gets you the function that is the derivative. Okay, and now you can use it over and over and over again to find the slope of a tangent line or the rate of change of the function at different points along the function. Okay, which is actually probably what you're going to want to do with it. You're going to want to find a sweet spot on your function, let's say. Where is it increasing the fastest? Where's the maximum? That kind of thing. Okay. All right, so this is just arithmetic, right? Here I've got a -4 plus a 3, okay, which is -1. And down here I have a -6 plus a 7, which is a +1. So this is -1/1, which is -1. Okay, and that's the answer to the question. Okay. So now that we've done 2 of these, let me ask any questions on either 1 or 2? Any questions on either 1 or 2? Okay, anybody not comfortable with some of the algebra? Feel free to ask. Okay. All right. That's the basics, actually. There isn't a whole lot more to doing this, but I think it would be a good idea if you tried it. Okay. Again, just so you know, I've been looking into trying to get a shareable, like a Jamboard or a whiteboard for our class. And I'm trying to figure out what's the best way to do this. Jamboard is like one board for everybody, and I think that would be kind of chaotic. Desmos has built-in whiteboards that everybody could get their own, but I have to figure out how to create a class code and what that would mean as far as our material is concerned. But I'm trying to figure out a good way to actually have you work so that we can all see what everybody's doing. Okay? Because I honestly think that's a lot more useful than working in isolation. Okay? So take a look at example 3. Okay? Now, the first thing I'm going to ask you is try example 3 and then stop when you get dy dx and type done in the chat. Okay, so don't bother evaluating. I just want to see that you can do the implicit differentiation. Okay, remember this can be written as 1/9 x squared plus 1/16 y squared equals 1. Okay, so I'm going to give you some time to do this one. And just please type done when you have what you think is an answer. Let's maybe take another minute to do this. All right, everyone. I know some of you are still working, and that's okay. But let's come together so we're all on the same page with how to solve this problem. I told you to start out by rewriting x squared over 9 and y squared over 16 with a coefficient out in front. Remember, dividing something by 9 is the same as multiplying it by 1/9. Dividing something by 16 is the same as multiplying it by 1/16. You might remember that from arithmetic as dividing by a number is the same as multiplying by its reciprocal. Okay, so basically that's what I did. Why did I do that? Well, it's a lot easier to pull coefficients out in front when you do calculus because you just pull them through the calculus operation. Okay, I don't have to worry about denominators. Okay, so I'm going to differentiate each term here. And again, the x term is just a normal x term. So I'm going to do it with the power rule, bring down the 2 and drop the exponent by 1. Now notice, okay, this is 2 over 1. So 2 is in the numerator, so is x. Okay, so I want to make sure everybody's comfortable with the whole fraction business. Okay, and then I'm going to do the same thing with the y term. The only difference is y is now a composite function. It's a function of x. So I'm going to use the chain rule on it. So first I'm going to differentiate y, and then I'm going to multiply that by the derivative of the inside function, which is dy dx. Okay, so that's that. And don't try to do the algebra as you're doing the calculus. Just do the calculus and come back and fix it. Okay, simplify it. The derivative of 1 is 0. So here's what I've got. I've got 2/9 x plus 2/16 y dy dx equals 0. Okay, here's another tip is don't mess with the fractions until later on. Okay, because this just may cancel out some stuff. Okay, so I'm not going to try to reduce 2/16 or any of that stuff. I'm just going to solve for dy dx. Now you can see I got two terms here, 2/9 x, right, and 2/16 y dy dx. This is the term with dy dx in it. This is a positive term, so I'm going to subtract that term to get it over here. Okay, and that gives me 2/16 y dy dx equals negative 2/9 x. Okay, everybody all right with that? Okay. Well, let's keep going with the simplifying. I want to get dy dx alone. That means I need to divide by this. Okay. Well, dividing by y is no big deal. That's okay. But if I want to divide by 2/16, the easiest way to do that is to multiply by the reciprocal. So think about it like this. And then I'm going to divide by y. All right, so here's the left side. Okay, I just want to show you that it works. Notice the y's cancel, the 2's cancel, the 16's cancel, and I'm left with 1. Okay, when they cancel out, they don't become zeros, they become 1s. Okay, now I have to multiply the right-hand side by the same thing, 16 over 2y, and that was negative 2x over 9. Okay, again, I'm explicitly writing the x in the numerator. Okay, so you know where the variables are. Okay, and you can see again, hey, look, the 2's cancel and I'm left with a negative 1x there. Okay, so I have dy dx equals negative 16x. That's what's in the numerator. I've got a 16, a negative sign, and an x, right? Convention says put the negative sign and the number out first, and then the variable, all right? And then on the bottom, I've got a 9y. All right, so there's my derivative dy dx. Okay, and they want me to evaluate it at 0, 4. Okay, that's going to be easy because I'm putting a 0 in the numerator. All right, so dy dx equals minus 16 times 0 over 9 times 4. Okay, anything times 0 is 0. All right, and 0 doesn't have a sign on it, so the negative sign becomes irrelevant, okay, because my answer is 0. There's no negative 0, it's just 0. Okay, so anybody have questions about that one? So at this point, 0, 4, this relation has a horizontal tangent line, right? Because its slope is 0, right? How about this? Any questions on this one? Questions on 3? Anybody, any problems with the fractions? Okay. I'm going to wait just a few seconds, see if anybody has anything. All righty. All right, let's take a look at this one. Here's a log inside a log equation. And again, this would require some fancy stuff with exponentials to solve. So let's just differentiate it implicitly. Okay, so anywhere I see a y, I'm going to generate a dy dx, right? This is a composition function, right? Its log is my outside function. And my argument is y, so that's a composition. It's a function of x. So first, let's differentiate the outside. So 1 over y. Okay, that's, again, the derivative of ln y. All right, and then I have dy dx. Okay, that's the derivative of the inside function. The next term is just a regular old x term, so its derivative is 3. Okay, the next term's a constant, so it gives me a 0. I'm just not going to write anything. All right, and then the derivative of 0 is still 0. Okay, understand, -7 and 0 are both constants. They give you a 0 derivative. Okay, if you want to write -0 here, you can. There's really no point to doing that, so I didn't. All right, so that's the calculus step. Now we get to isolate dy dx. So first I'm going to subtract 3 from both sides. That gives me 1 over y dy dx equals -3. Okay, and then the last thing I need to do, since y is in the denominator here, I'm going to multiply both sides by y. And you can see that makes the y's cancel. And I'm left then with just dy dx equals -3y. Okay, and they want me to evaluate it at the point 2e. So all I have to do, since 2 is x, there's no x in my derivative, I'm just going to plug in e for y. Okay, and believe it or not, -3e is just a number. Remember, e is approximately 2.7. Okay, so this is a number that's approximately, oh, I don't know, -10-ish. Okay, basically, you just leave the E in here. This is an exact answer, but E is not a variable, okay? So basically this is your exact answer. Don't approximate E, just leave it like this. Okay, so any questions on 4? I'm trying to show you as many flavors as I can. Okay, but all of these they lean heavily on your algebra skills. Okay, because again, what you're going to do is simplify things before you even get started. Like for example, if you look at number 5, I'm going to write this as x to the 1/2 plus y to the 1/2 equals 5 before I even start. Because again, calculus is friendly to coefficients and powers. Okay, so I'm trying to rewrite my relation so it's got coefficients and powers. Okay? All right, well, differentiating this one, the first term is just an x term, so this gives me 1/2 x to the minus 1/2 using the power rule. Okay, the next term's a y term, so it's a composition. First differentiate the y, which gives you something that looks really similar. And then you differentiate the inner function dy dx, and the derivative of the 5 is a 0. Okay? And again, you can do this any way you want. Some people change the square roots at this point. I like to keep them as exponents, so then I know what I'm doing. Okay? So notice I have a term with dy dx in it, so I need to get this term on the opposite side. So I'm going to subtract it. All right, so it cancels out over here. And I'm left with 1/2 y to the minus 1/2 dy dx equals negative 1/2 x to the minus 1/2. Okay, so that's the first algebra step. Okay, the second algebra step requires that I divide both sides by 1/2 y to the minus 1/2, right? Because I want to get rid of that. Okay, now you can think of doing it like that. Okay. All right, and you can do it like this and realize, okay, this whole thing cancels out, leaves a 1. What happens on the other side? Well, the 1/2s obviously cancel out, okay, but the negative sign stays on top. Okay, that's one way to do it. And again, I'm only doing it this way. This is kind of like the lazy man's way, okay, because they're the same value, just with different signs. So this gives me negative x to the minus 1/2 over y to the minus 1/2. Okay. Now I'm to the point where, all right, maybe I want to put this more like square roots. Okay, because I'm looking at the point I have to substitute in, and that looks like taking a square root. There is nothing wrong with leaving it like this and evaluating it like this. Just make sure you don't lose any negative signs. But here's another way you can do it. Okay, x to the 1/2 is a square root. X to the negative 1/2 means that the square root is on the opposite side of the fraction bar. Okay, so the very first thing I'm going to do is, since I have a negative sign in my numerator but not my denominator, I'm going to move it out in front. Okay, remember, negative divided by positive is negative. So I'm just pulling the negative sign out front. If both of these were negative, I could call the whole fraction positive. Okay, but I'm just pulling this negative sign out in front so it doesn't get in the way. And then I'm going to put the square root of x on the bottom. Okay, so negative, the 1/2 exponent makes a square root, the negative 1/2 flips it on the other side. Likewise, this y to the minus 1/2 is going to give me a square root of y, but on the opposite side of the fraction bar. Okay, so this is everything simplified out. And then all you have to do is evaluate it at 4, 9. Okay, and then I have dy dx equals the negative square root of 4 over the square root of 9. Okay, which is did it backwards, didn't I? Yeah. Plug y. Here's x, here's y. I'm plugging in y on the top, so there's 9, there's 4. Okay, I've got a y on top, so there's the y value going in on top. I've got the x on the bottom, there's the x value going in. Taking square roots gives me a negative 3 over 2. Okay, so that's the slope of my tangent line at the point 4, 9. It's also the rate of change of this function's y value at that point. Okay, so those are all the flavors that I was able to think of that you might run into. Okay, so any questions on 5? Questions on 5? Okay, most of the weirdness in this question was not the calculus at all. Okay, it was the algebra. Okay. Any questions on 5? Okay, not seeing any. Okay, so there's a couple of more problems here. I'll work them out for you so you can see how they roll. But I'd like to move on to the related rates stuff. Okay, because that's how you're actually going to apply this. Okay, so related rates says if you've got a bunch of quantities that are related to each other and they change at a known rate with respect to time, we can determine how all the other quantities are changing with respect to time. Okay, so again, with respect to time, t, okay? So basically, if you want to do all of these problems, okay, identify the quantities that are changing and assign them variables. Find an equation that relates those variables. This is usually the hard part, okay? Differentiate both sides of the equation with respect to time. So let's say you have x, y as your variables. You're going to have dx, dt, and dy, dt. So how is this different from before? Well, before, we were just thinking of y as a function of x. In related rates problems, all of your variables are functions of time. So say both x and y are functions of time, okay? So every time you differentiate a variable now, there's no more free rides, okay? You're always going to have to treat them as compositions. And so you're going to have the derivative of the outside, and then you're going to have either dx dt, dy dt tacked onto it, okay? So all variables are functions of time, okay? Again, that's functions of. Okay, does that make sense to people? Makes sense? Okay, there's no point in launching into examples if the whole concept doesn't make sense. Okay, so you can think here's a classic type of a problem. Suppose you have a leaking oil tanker, and we'll do one like this. Okay, it's spreading a circular oil slick. Well, that circular oil slick has a radius that's changing with respect to time, right? And so is its area changing with respect to time. Okay, and those two things are related, right? By area of a circle is pi r squared. So if we know how fast the slick is spreading, or how big the radius is, how fast the radius is changing, we can get an idea of how much surface area of the ocean that slick is covering, which might be important if we're the guys who have to clean it up. Okay, so you can kind of see where related rates are used. Okay. So I'm going to pick and choose There's a whole bunch of related rates problems in this section. So I'm going to just pick and choose a couple so you can see how they work. Okay. As again, I promise when I upload the notes, I'll have all of the problems worked out so you can see all of the different flavors. Okay, so let's start with this one. Okay, an expandable sphere is being filled with liquid at a constant rate from a tap. You should be thinking water balloon connected to a faucet. Okay, and you know, if you fill up a water balloon, it goes from being like pretty limp to being bigger and bigger and bigger and bigger. And we're not going to like burst it or anything, but we want to know how much, how fast are the things changing. Okay, so we have a sphere and its radius is 3 inches. Okay, so I'm going to draw an idealized balloon that's a sphere. Hold on. There you go. And then we'll put, whoops, I didn't need to move it like that. So move it back, make it smaller. Okay, and then I have, here's kind of letting you know it's 3-dimensional. Here's its radius, R. And we're going to say it's 3 inches. Okay, so there's our balloon with a 3-inch radius. Okay, they are kind enough to give us the formula for the volume of a sphere. Okay, so here is the formula for the volume of a sphere. Okay, what else did they tell us? Well, they tell us that the radius is increasing at 2 inches per minute. Okay, well, what is that? That's the change in the radius with respect to time. Okay, so dr dt is 2 inches per minute. Again, you're not going to need the units when we're actually working the problem. We're going to put the rates in without units, but it's important when you interpret the results, okay, that you have the proper units in things. Okay, now, this is probably the hardest thing to do, okay? How fast is the liquid coming out of the tap? Let's assume it's water. How fast is the liquid coming out of the tap? Okay. What are they asking you for? Okay. Is it a rate? What are they asking you for? Is it a rate? How would you tell? Okay, this is a kind of a, how do I know what they're asking me for? Anybody have any thoughts? Okay, my first question to you is just, is it a rate? And how do you know if it is or it isn't? Okay, you can unmute yourself and ask, folks. You don't have to, you know, just type in the chat, particularly if it's long. Anybody thoughts? Is this question asking you for a rate? And if so, how do you know? Okay, so Ni is saying, yes, it's a rate. And again, what gives you the clue is this word right here. How fast is the liquid coming out of the tap? Well, I don't know how fast the liquid's coming out of the tap, but I do know the volume of liquid coming out of the tap is what's filling the balloon. Okay, is what's filling the balloon. Okay, and everybody should have a rough idea of how this works, right? If the radius of the balloon is getting larger and larger and larger, so is the volume of the balloon, right? And what is taking up that volume? Well, the liquid that's coming out of the tap. Okay, so as Ni is saying, it's the volume of water. You're interested in the rate of change of that, okay? So you need to find dV dt of the balloon's volume. Okay, you need to find the rate of change of the balloon's volume. So in other words, the water that's coming out of the tap is filling up the balloon. So to find how fast the liquid's coming out of the tap, and that's going to be in what? Well, it's going to be, you're measuring the radius in inches and you're measuring time in minutes, right? Your rate is going to be cubic inches per minute. And yes, they do measure water that way. Okay? It isn't always measured in gallons and quarts, okay? It's measured sometimes in volumes, okay? Does that part make sense? Does that much make sense? Okay, so we know what we're given, okay? We have that givens over here, a radius, a spherical balloon, and a rate of change of the radius. We know what we're trying to find, and they gave us the formula that relates all of that. Okay, so let's start with this. Volume is 4/3 pi, okay, r cubed. Volume is 4/3 pi r cubed. Now we're going to differentiate everything implicitly, okay? We have two variables that change with time, the volume and the radius. This business here is just a constant. Remember, pi is just a number. Okay, so if I'm going to differentiate v implicitly, I get 1 times dv dt. Again, my variable I'm differentiating with respect to now is time. This part's a constant, so I'm just going to pull it through. And then I have r. R is also a function of time, so I'm treating it like a composition with the chain rule. I'm going to differentiate the outside. Okay, so that's the power rule, and then dr dt. Okay, and if you think about it, okay, I don't need the 1 out here. That's not doing me any good. So I've already solved for dv dt. Yay, that's what I was looking for. Now I have to make sure I have all of the variables on this side of the equation. 4/3 pi is just a number, don't need anything there. I have the radius, because they told me when the radius is 3 inches, so r is going to be 3. And they told me the rate at which the radius is changing when it's 3 inches. So I have dr dt. So I'm good to go. Okay, so I have 4/3 pi times 3 times the radius squared times dr dt, which is 2. Okay, again, I said I wasn't working with units, but if you take a look at this much is going to be in inches, and then you're going to square it, so you're going to have square inches. This is going to be inches per minute, so you're going to have inches squared times inches, that's cubic inches per minute, which is the right units for a rate of change of volume, right? So cubic inches per minute are going to be what our answer is in. Okay, everybody all right with that much? So then the rest is just plug it into a calculator, right? 4/3 pi times 3 times 3 squared plus times 2, just plug it in. Again, if I bring up my TI and I share that with you, you'll see how that works in turning it on, clearing it. Okay, so I have 4/3, and I always use them as fractions. Okay, and then pi times 3 times 3 squared times 2. Okay, so I'm just evaluating it on a calculator. Okay, and I get an approximate value of about 226 cubic inches per minute. Okay, everybody all right with that? Anybody have any questions about that? All right, and again, if they asked you to have an exact answer, okay, this is an approximate answer, right? Because we had to round pi. If they asked you for an exact answer, you would just multiply everything but pi, right? You could multiply 4/3 times 3, so you get 4 times 3 squared times 2, which I think is 72, 72 pi, okay, cubic inches. Okay, so I want to point something out. Notice I used an equal sign here, all right? That's because this is an exact answer with pi in it. Okay, all I did was multiply all the numeric parts together, okay, and the pi's coming along for the ride, okay, because the symbol pi has its infinity of decimal places along with it. So this is an exact answer, all right, and this is an approximate answer once you plug in an approximation for pi, okay? We're not quite on the money anymore because you're chopping off some of the decimal places of pi. Okay, everybody okay with evaluating the answer? Okay with evaluating the answer? Okay, so there's one that involves a volume of a sphere. Okay. Anybody questions about it? I want to see just how much time we have. Okay. We might be able to do 2 more. Okay, but again, I'll certainly upload the rest for you. Okay, so let's take a look at example 8. Okay, example 8 is a variety of problem that's really common with related rates. It's sometimes called the sliding ladder problem. Okay, you have a triangle where 2 sides of it are fixed. You can think of this as being a building and the ground. Okay, and then you have a ladder, right? And it's basically sliding down the wall. Okay, so the bottom is coming away from the building, and then this is sliding down the wall. Okay, and nothing's changing length. Okay, so you've got a 16 and a 12. Okay, so maybe the first thing you probably need to do is figure out how long is this red thing. Okay, the red side of the triangle. Okay, so again, nothing's changing length, but what is changing is the area of the triangle. Okay, and so is the perimeter changing. Okay, so basically this is sliding down, and I guess what's happening is, yes, the 16 is going to get smaller, the 12 is going to get bigger as this slides around. Okay, so it says the base of the triangle is growing at 3 inches an hour. Okay, I'm going to call this direction X, and I'm going to call this direction Y because you're used to seeing it that way, and I need to minimize the chat. Okay, so if you have anything you want to say, please unmute and just ask or say it. Okay, I don't have the chat open. So again, if the base is growing at 3 inches per hour, okay, then what do I know? I know that, well, dx dt is 3. Okay, so that's getting bigger as this slides out. Okay, and then dy dt is shrinking, right? So this is dy dt. And they're telling me it's shrinking at the rate of 3 inches per hour. So that would mean that it's a negative value. So dy dt equals -3. Okay, so that's taking the information from the problem and actually labeling the diagram with it. Okay, the other thing I'm interested in, because I probably am going to need it, is this length over here. Again, not quite sure if I need it or not. Okay. But I could use the Pythagorean theorem to find it if I need it. Okay, but the relationship that is going to relate these parts is going to be, okay, this is going to be the square root of x squared plus y squared. Okay, you might remember that from the Pythagorean theorem. This part's called the hypotenuse, and it's equal to, you think of it as c squared equals x squared plus y squared. Well, if I want just c instead of c squared, I take the square root of x squared plus y squared. Okay? All right, and when both of these values are set at 16 and 12, what would this be? Okay, this would be, this is something you evaluate with a calculator, and you get 256 plus 144, which is 400. And the square root of that is 20. Okay, so right at this instant, this red line is 20 inches. Okay, so I've already just like taken all of the information given in the problem, the two rates of change for the sides, okay, and then I'm using the Pythagorean theorem to find this missing side. Okay, the next thing I have to ask is, what about area? Okay, they're asking me about area. So I need a formula for the area of a triangle. You might remember area as 1/2 base times height. Okay, and in my example, my base is called x and my height is called y. So that's how I would write this formula. Okay, here's the base of the triangle down here. Here's the height of the triangle, and it's a right triangle, so that's easy, right? So I need to know if the area is increasing or decreasing. So what I need to find is dA dt. Okay, and what I need to find out is the sign on dA dt positive or negative? Okay, if it's positive, that means the area is growing, right? If it's negative, that means the area is shrinking. Okay, so I'm going to take the derivative of 1/2 xy. Okay, and again, it's a product. Okay, both of these are functions of time. Okay, so let me see if I can do this here. I'm using the product rule first, and then I'm going to use the chain rule inside of each, okay? So part of my problem is I'm running out of space here. Let's call this U. Let's call that V. Okay, so then I have U prime. One half, right? The X disappears, okay, because I'm using the power rule. And then dx dt. V prime equals y. Y disappears, right? I just get a 1. And then I get dy dt. Okay, and then you put them together in the product rule, u times v prime plus u prime times v, okay? And you're going to get 1/2 x dy dt plus u prime is 1/2 dx dt, and the v is going to go in the middle there, which is the y. Okay, so that's, again, differentiating this using the product rule first, and then the chain rule inside. Okay, So basically, everybody okay with that? Okay, so here's what I have. Okay, all I did was take this result from the product rule, bring it over here, and I factored out the 1/2 to make it easier to do arithmetic with. Okay, and then all I need to do is to plug in my numbers. I have 1/2. Okay, x is 12. And the rate of change of y is a -3. And then I have my y, which is 16, and the rate of change of x is +3. Okay, and if you work this out, you can see 12 times -3, okay, is what? -36. And 16 times 3 is 48. Okay, again, it doesn't matter what the number is. Okay, it's a positive value. So it's in area is increasing. They're not asking me how fast it's increasing or decreasing, but I know it's increasing. Okay, because it's a positive value. Does that make sense to people? Okay, I'm trying to put a summary in the chat. Positive DABT means the area of the triangle is getting bigger. Okay. Now, again, the last half asks for perimeter. I'm not going to work it out because we're running out of time. But perimeter is just the sum of all the sides of the triangle, right? So that's x plus y plus the hypotenuse. Okay? And if you want to find out whether that's increasing or decreasing, you're going to need to find dp dt. Okay? See if the sign is positive or negative. Okay? Again, this is just a chain rule inside a chain rule, right? You're going to rewrite this as parentheses with a 1/2 on here. Okay, so again, I'm going to skip this half. I'm just showing you how to set it up. Anybody got questions on that one? No? Okay. Everybody understand why if the rate of change is positive, it means something's getting bigger? You know that, right? Positive derivatives mean something's increasing. Negative derivatives mean something's decreasing. Okay, so that's where that's coming from, right? I want to make sure that this is sensible to you. Do the applications make sense? All right, they have to make sense to you. Now, I admit nobody's going to ask you to like time a triangle increasing or decreasing. But again, it's more commonly portrayed as a sliding ladder. Okay. All right, I have one more I want to show you, example 11. Okay, and again, we may not have time to actually work the whole thing out because we're already at 20 after. Okay, but let's just talk about it. We have an oil tanker in Puget Sound up near Seattle has sprung a leak and a circular oil slick is forming. The oil slick is 4 inches thick everywhere. It's 100 feet in diameter, and the diameter is increasing at 12 feet per hour. So here's what we've got. Okay, this part is 4 inches. Okay, or 1/3 of a foot. Okay. How do I know that? 12 inches in a foot, 4/12 is 1/3. Okay. It's 100 feet in diameter. So this is 100 feet. And the diameter is increasing dt at 12 feet per hour. Your job as the Coast Guard commander or the tanker captain is to determine how fast the oil is leaking from the tanker. Okay, well, what you've actually got, if you want to think of it, is a cylindrical oil spill, right? The surface of it is a circle, and then it's so many inches thick on the water, and which is, this part is not realistic. They're saying it's the same thickness everywhere. A real oil spill doesn't behave that way. Okay, it's thinner at the edges, okay? But they're trying to simplify the problem. They're also telling you it's not, the thickness is not changing. Okay, so what you want to think of is I have a cylinder. And what I need to figure out is the volume of it. Okay, the volume, and what they're saying is you're assuming whatever's leaking out of the tanker is winding up in the oil slick. Okay, so you've got a volume of the cylinder, which is, again, its area of the base times the height. Okay, and what you want to find is, rather than V, you want to find dV dt. You want to find out how fast is that oil coming out of that tanker. Okay, so my area of my base is pi times the radius squared. Okay, all right, and the height we said was, 4. But let's just put in H for now. Okay, so that's our volume of a cylinder formula. Okay. The other thing is they've given us a diameter. Okay, so radius is diameter over 2. Okay. All right. So let's see what I've got here. I've got pi times my diameter over 2 squared times height. Okay. Again, why am I doing it in terms of the diameter? Because they gave me a rate of change for the diameter, not the radius. Okay, so I'm getting everything in terms of what they gave me. Okay, so if you take a look at this, okay, this simplifies a bit. Okay, this will give me pi times d squared over 4, right? What did I just do? I squared the d and I squared the 2 times height. Okay, so if I want to find the rate of change of the volume, the first thing I can pull through is the constants, which is pi and 4. All right, then I'm just worried about differentiating d squared and h. Okay, and again, if I can do that with my product rule, I'm doing it off to the side here. Okay, so u is d squared, v is h. Okay, they're both functions of time. Okay, now there's going to be an insight here in a minute. Okay, u prime is 2d dd dt, right? Because the diameter is a function of time. Okay, so you're going to treat it like a composite function. You differentiate the d squared, then you differentiate the inner function, the diameter. Okay, and then over here, when we do v prime, we're going to get a 1 times dh dt. Okay, and the product rule is u times v prime plus u prime times v. Okay, so d squared times dh dt plus 2d dd dt times h. Okay, now they told you some stuff that will help simplify this. Okay, but let me put it in over here just so you can see. Okay, so there it is going into my overall derivative. Okay, so this is just the product rule. I pulled through all the coefficients first, get the pi and the 4 out of the way, and then I'm just differentiating d squared h. And again, why am I using d instead of r? Because they gave me a rate of change in terms of d, not r. And you can't just have it. That's not the way rates work. Okay? All right, so that's what I have. All right, now let's see if I can plug some stuff in based on the story problem itself. This is pi over 4. Okay, the diameter squared is 100 squared. The diameter is changing, okay, at what rate? Well, this is not diameter, this is height. And they told you that the height is the same everywhere and the height isn't changing. Okay, so your dh dt is 0. And again, if your height is constant, that's what they're telling you in the story, okay, you're not plugging in anything there. Okay, you're not plugging in anything for the dh dt. Okay, then you have 2 times the diameter's value, and then the rate of change of the diameter, okay, which is okay, I lost my h over here. I forgot to copy my h. Yeah, there you go. Okay, so basically they're saying it's increasing at the rate of 12 feet per hour. Okay, and then I have to multiply by my height in terms of feet. Okay, you got to make sure all your units are the same. Why don't we multiply h in the product rule? Okay, I'm not quite sure I understand. It's down here. Okay, so if this is d squared, differentiating it gives me 2d dd dt. Okay, the h gives me 1 times the h dt, and then I'm following the pattern here. Okay, so the u is d squared, and then the v prime is just dh dt. The u prime is 2d dd dt, and v is h. So I guess I'm not sure where you mean. So can you ask it a little differently? Question differently. I'm not sure where you mean. Okay. So I have an H in my product rule. It does come out. I just lost it when I copied. Okay, so there is an H in here. And it comes from here. Okay, does that make sense? Okay, anybody else not following where everything's coming from? Okay, again, when I copied it over here, I lost the H that's over here. Okay, so I added it. Okay, so there is an H. And again, the trick is to make sure that all of your measurements are in the same units. That's why I changed my 4 inches to 1/3 of a foot, because everything else was in terms of feet. Okay. All right, then it's a matter of just multiplying everything out. This term disappears, and you're going to have 200 times 4, so that's going to be 800. So this much is 800 pi over 4. okay, which is, if you want to do it this way, you could say 200 pi cubic feet per hour. Okay, I just divided out the 4 there. And if you, that's the exact answer. But again, the captain or the Coast Guard is probably not going to be too thrilled with pi. Okay, so we can approximate this by plugging in an approximation for pi. And I get 628 cubic feet per hour. So again, what this is saying is oil's coming out of the tanker at the rate of 628 cubic feet every hour. That's a lot of oil. Okay, so again, strategy here was there were 2 things you had to watch out for in the beginning. The first thing was make sure all of your measurements are in the same units. The other thing was make sure you express your area of the cylinder's base in terms of the diameter, since that's what they gave you. Okay, and then it was just a matter of differentiating the volume formula to get dV dt. Okay, and then the rest of it is pretty straightforward. So let me ask questions on 11. Any questions on number 11? Anybody? No questions? Okay, you can see the rough part about these problems is figuring out what's given to you in the form of rates. Okay, all of the rates will have dt in the denominators. And then the other trick is figuring out what is the relationship among all these. Okay, so this one required you to visualize the oil slick like a cylinder floating on top of the water. Okay, that is by far the hardest part of the problem, is figuring out what to use. Okay, how do you get good at them? You practice. Okay, you look at a lot of examples and you practice them yourself. Okay, so there's no magic. All right, I'm going to stop sharing, come back to the meeting, and ask if you have questions on anything. Questions on anything? Okay, whether we shared it today or not.